Hi everyone, welcome back. It's amazing how much trouble people have with scalar projection. Let's forget about all the super duper diagrams and everything. Just go back to the basics. I like to talk about the Mr. Bean method. Mr. Bean in one of his TV shows was measuring how to put an air conditioner in and cutting a hole in the wall, and he measured like this. Just rough. I find incredibly powerful that concept of just doing it rough. No super duper gizmos and all that sort of stuff, just doing it rough. So I've got an I plus a 4j. So all that means is I go across 1 and up 4. So across 1 and up 4. So if I start here, let's not go X, Y axis or Argand diagrams. Just want to go across 1. I don't go across that far. There's 1 across. Now I've got to go up 4 using that. So about 4. Maybe I'll make it a bit smaller. There we go. 1, 2, 3, 4. And of course when I look from here, so you can see they're actually different sizes. But, you know, I'll try to do it better. 1, 2, 3. As you're looking at the whiteboard, it's awkward. So that one there would be, oh that's nice, I plus 4j. And I could call that vector A. And some of you are watching, some of you will put a little vector symbol above it. You can put it below it. Or you can do it in just bold print, which we can't do on the board. Now this one's 8i plus 6j, so I'm going to try to be reasonable. 2, 3, 4, probably be more careful than usual. 1, 2, 3, 4, 5, 6, 7, 8. I'm going to go up 6. 1, 2, 3, 4, 5, 6. Try to draw that inaccurately. Oh, beautiful. So this one I could call vector B, which is 8i plus 6j. Let's have a look what's going on here. Now, everyone tries to talk about scalar projection. How do I get the scalar projection of this vector onto that vector? It means if I go to the tip of that vector and I come across at right angles to this one here, this length here from there to there is called the scalar projection of A onto B. And I could write up the words scalar projection of A on B. I could write it in shortcut ways, but I just want to look at that we're finding that length there. So if I just ignored all the stuff about scalars and we just had this little diagram here, I can talk about finding that X there. Now before I find that X there, I need the length of this side. How do you find the length of any vector? I'm not going to go into detail here. It's Pythagoras Theorem. You can have a quick look here. You can see the length of this uses a 1 and a 4. So all I'm going to do is go 1 by 1 is 1, 4 by 4 is 16, add them together, and the magnitude of vector A is the square root of 1 plus 16, which is root 17. So I now know I've got a triangle here with, I'm finding X, that's a root 17, and I calculated previously that the angle between those two vectors is 39 degrees. So how do I get that length there? Here's the adjacent and the hypotenuse. Most of you are okay with it. So this is a cos 39 degrees equals the x on root 17. Of course I can rearrange that and have it as x equals root 17 cos 39 degrees. Let's have a look at what we've got here. So x is the magnitude of this vector here, the magnitude of A, times by the cos of the angle in between, that angle there, in this case was 39, cos of that angle there. So this is always going to be the magnitude of the one you're projecting from and the angle that's in between. So simple rule. Nothing to do with vectors, it's really just trigonometry. Now when we put the numbers into that, I've stored it over here and I've got it as 3.2. Now here's the wonderful thing. Here's the part where your brain starts to connect the different concepts. There's a thing called a dot product. Dot product is A dot B equals the magnitude of A by the magnitude of B by the cos of the angle in between them. So let's have a look what's happening here. This says the magnitude of A cos theta. So over here we've got the magnitude of A. Oops, red pen's had it. We've got the magnitude of A and we've got the cos of theta. So if I want magnitude of A cos theta, if I divide this by the magnitude of B, I divide that by the magnitude of B, and this is another expression for the scalar projection. So let's have a look at what that scalar projection is. Let's have a look at it then. Instead of writing A, this cancels out. Instead of writing A dot cos theta, we can go A dot B on the magnitude of B. And there'll be people out there watching going, oh, that's A by the unit vector B. Let's forget about that for the moment. Let's go through what this is. Instead of calculating that way when you know the angle, so this is knowing the angle, this is when you don't know the angle. So here's the knowing the angle method. That's the angle method. And here's the two vectors method. So on this question I know the two vectors. If I knew the angle would be okay, but often you don't know the angle, you can work it out. But we just want to use this method instead. Let's have a look at what happens here instead. So instead of doing it that way, I can go A dot B. Now the interesting part is always the magnitude of B, which is the one that's projected onto. So let's have a look at it. So the rule is A dot B on the magnitude of B. So I'm going to write that A as 1/4. I prefer that for the calculations. You can write it the other way if you want to. And we want to multiply that by 8/6. If you're not used to writing it that way, instead of writing I plus 4j that way, we're allowed to write it that way. There's other methods as well. And we're going to divide it by the magnitude of B. How do we get the magnitude of B? You can see it here. That's across 8 and up 6. You can use Pythagoras Theorem. If you know your Pythagorean triads, which is the reason I did it, is 8 and 6 becomes 10. But if you didn't know that, you'd put the square root of 8 squared plus 6 squared. Now remember we're looking for an answer of, oh, I wrote 3.9 over there. An answer of 3.2. Oh my goodness, of mistakes. Here we go. To calculate a dot product, you just go 1 times 8 is 8, 4 times 6 is 24. Could look at that on other vectors, y. The other numbers drop out. We don't need the other numbers. This is the square root of 64 plus the square root of 36. So that's just the square root of 100, which is 10. And we come up with an answer of 32 on 10, which is 3.2, which is the same as the answer we're looking for there. Oh my goodness, this drags out as a video. I think I'm going to cut it short there. I'll do the next example. Hopefully there's a very short video and a little bit more common sense. So if it's just starting to sink in, this is the length going from one point at the end of a vector onto another vector, and that length there is called the scalar projection. In other words, the amount of that vector that would fit onto there if we come across perpendicular to it or at right angles to it. Thanks for watching. I'll make another one in a minute.